Okay, fine. So I just hope that I'm audible. So first of all, please let me know in the chat window. Good evening, everyone. So just let me know in the chat window whether I'm audible or not, and also whether the screen is visible or not. In case everything is working fine, then we can just go ahead and start with today's class. Good evening. Am I audible? Hello. Okay, fine. Okay, and what about the screen? Okay, if everything is working properly, then we can just get started now. Okay, so in the last class, I actually told you this now that we are lagging a bit behind, and that I'll be taking 1 hour class, but I couldn't really like take out time from today's schedule. So I'll be like so in this class we'll be continuing with heap, and then we'll be jumping over to linked list and stacks. Fine. So in the last class we were discussing about AVL trees, and we did look at this, that what all operations do we actually perform whenever we have this LL unbalanced node, RR unbalanced node, LR unbalanced node, and RL unbalanced node. Fine. So these were the four cases of unbalanced node, and how do we balance these kind of nodes. That is what we discussed in the last class. So I'll be now discussing only a few examples about these unbalanced cases. So let's say that we are having this particular tree. This particular tree. Okay, so this is actually not balanced. So this is actually not an AVL tree right now, right? Because this particular node is not balanced, because the height of left subtree is 1, 2, 3, and the height of right subtree is only 1. So this is not an AVL tree, so I'll just make it an AVL tree by adding this particular node. Fine. So now this particular tree is an AVL tree. Fine. So now let's say that we have this particular AVL tree, and we want to insert 11 in this particular AVL tree. Then how do we insert 11? So we'll just go ahead and just follow the BST procedure, and we'll go ahead and add. So we compare 11 and with 12, so we know that we need to go to the left. So we compare 6 with 11, and we know we need to go to the right. So we compare 11 with 9, and we know that we need to go to the right. And then we compare 11 with 10, and we know that 11 should come to the right of 10. So fine. Right after this particular insertion, what do I do is that I'll trace my path back to the root, and while tracing this particular path, I'll see whether some node is unbalanced or whether there is any unbalanced node or not. Fine. So on this particular path, I'll check all the nodes. So this is balanced, this is also balanced. What about this particular node? This is also balanced, because the height of left subtree is 1 and the height of right subtree is 2. So 1 minus 2 mod 1, mod is equal to 1 only. So this is also balanced. Now coming over to this particular node, this is actually not balanced. Why? Because the height of the left subtree is 1 only. But what about the height of the right subtree? It is 1, 2 and 3. So 1 minus 3 mod is actually equivalent to 2. Fine. So this is actually not a balanced AVL node. So after we have found out whether this particular node is balanced or not, so now we need to find out the type of the unbalanced node. Fine. So how do we find out the type of the unbalanced node? We know that this is the path that we took, right? And this is the path that we took. This is how we were tracing back. So the unbalancing came from this particular path, and this particular path is left child, then again left child. Fine. So while we are tracing the path, so from whichever path we are coming back now, so on that path, that is actually the path which caused all the unbalancing thing. and that is how we identify the type of my unbalanced node. So this is right right, so this is right right, so this is, so you just need to check two levels of children only. So this is right children and then again it is right children. So this is the tree which is actually causing the unbalancing thing. Fine. So after you have got the type of the unbalanced node, after you have got the type of the unbalanced node, we just need to perform the appropriate rotations. Fine. So we will actually just go ahead and perform the appropriate rotations. What are those rotations? I actually like told you this, that in case of RR we just need to apply an anti-clockwise rotation on my unbalanced node. So in case of RR I just need to apply anti-clockwise rotation on my unbalanced node. So this was the node which was unbalanced, so I just need to apply anti-clockwise rotation. So how will I apply anti-clockwise rotation? There are mainly two pointer changes that will happen. 9 will come up, 6 will go down, and this particular child of 9 will be made the right child of 6. So one pointer change. So this is how I'm just drawing the tree here, because 9 will go up, 6 will come down. So this is how anti-clockwise rotation happens, right? Fine. And after this, whatever was to the left of 9 will become the right of 6. Sorry, this is 11. Fine. So this is how balancing happens in case of RR unbalanced node. Fine. So this was easy because there are only two pointer changes. One pointer changes, that this particular pointer changed and this particular pointer changed. So these two pointer changes only are the only pointer changes that happen in anti-clockwise rotation. Fine. So I just hope that now you can see that my ABL tree is now again balanced. So this is how we insert 11. So now I'll just rub this up and we'll see that how do we do the insertion of 7, this particular node. Fine. So this was the case of RR. Now let us just see that what happens when we try to insert this particular node 7. So this is I hope that this is like looking easy only, because there is nothing much, but you will actually like get more well versed with it only if you like practice a few questions, and in case of any doubt you can just go ahead and ping me anytime. Fine. So so this is I need to insert 7 now. So 7 is will go to the left of 12. So we come over here. Now 7 is actually greater than 6, so it will go over here. So we come to the right of 6. So now after comparing 7 with 9, we know that we need to go to the left. So after coming over here, we know that we need to go to the left subtree. So that is where we actually insert 7. So now I just need to follow this path, and I need to see on this particular path, I need to see that is there any node which has got unbalanced. This is what I need to see. So from my newly inserted node to back to the root. So this is the path which is actually being formed. So on this particular path, I will check that whether any node is unbalanced or not. Fine. So we'll just do that, but let me just like clear this thing. Okay, fine. So now over here I just check whether this particular node is balanced. Yes. This particular node is balanced. Yes. This particular node is balanced. Yes. Now coming over to this particular node is not balanced. Why? Because the height of left subtree is only 1 and the height of right subtree is 1, 2, 3. Fine. So 1 minus 3 mod is actually equivalent to 2. So basically this is this particular node is not balanced. Now how will I find out that which kind of unbalanced node it is? So what all I simply need to do is that I'll again just build that particular line on which I was tracing, right? So I was like following this path now, this particular path, and I was checking all the nodes on this particular path. So I need not like draw the whole part, but I just need to draw my path till from the newly inserted node to the node which is unbalanced. So this was the path, right? So here I can see that my first, on this particular path, I am having first as the right child and then I am going to the left child. So this particular node is actually RL unbalanced. This particular node is RL unbalanced node, and we know what all operations do we need to perform in case of RL. So first of all, we will convert RL. So how do we balance an RL unbalanced node? First of all, we convert it to RR. How do we convert it to RR? By applying clockwise rotation on its right child. So on this particular child 9, we will actually apply clockwise rotation. So we convert RL to RR by applying clockwise rotation to right child of unbalanced node. So you must take a note of this, that in case of RR we were actually applying all the rotation on the unbalanced node only, but in case of RL we will first convert it to RR. How? By applying the clockwise rotation on the right child of the unbalanced node, not on the unbalanced node. We'll be applying the rotation on the right child of the unbalanced node. So this is where we will actually apply our rotation. So after applying the rotation on this particular node, my 9 will come down and 8 will come up. So this is how my tree will look like. 8 will come up and 9 will come down. Fine. So this has been converted to RR, because as you can see that this is also balanced, this is also balanced, and now the unbalancing is coming from this particular path. Fine. So after doing this, after converting it to RR, we already know that how can we now convert it, how can we, so now we are having this particular node as RR unbalanced node, and now we know that how do we balance an RR unbalanced node. How do we balance it? By applying anti-clockwise rotation on the unbalanced node. So we actually apply the anti-clockwise rotation on my unbalanced node, which is 6. So after I apply anti-clockwise rotation on this, this is how my tree will look like. 8 will come up, 6 will come down. So my 8 will come up, 6 will come down, and the left child of 8 will become the right child of 6. So this particular pointer and this particular pointer are changed. These two pointers are the only pointers that are changed. Rest, everything remains the same. Fine. So this is how I do the balancing in case of RL node. So I'm not actually taking the example of LL and LR now. So I just hope that you will be able to do LL and LR. In case of LL, we simply apply the clockwise rotation on the unbalanced node. In case of LR, we have to first convert it to LL. How? By applying the anti-clockwise rotation. By applying the anti-clockwise rotation on the left child of the unbalanced node, and then we know that how do we balance an LL unbalanced node. Fine. So we actually took an example of this in the last class also. So I'm just like moving ahead quickly onto heaps. Fine. So I'll just first clear this particular slide, and then we will start discussing about heaps. So in case you are having any doubt, the last example that we after was on the right. So in case you are having any doubt, maybe is Sakshi having any doubt? In case you are having any doubt, you can like write that down in the chat window and I'll try to address that particular doubt. In the last example, Sakshi is saying that in the last example that we did yesterday, after rotating clockwise, 6 was on the right of 7. Okay, in the yesterday's class. Okay, how will I know that what happened in the last class? Okay, Sakshi probably like Sakshi, in case like you are having any doubt, you can because I'm not able to like get that particular doubt, I'll probably like reach out to you personally. In case you can reach out to me personally in case you are having any doubt. Fine, so probably I'll just move ahead right now. Okay, in the last class BST property was violated. Okay, fine, I might have like got something wrong. Okay, this particular thing. Okay, yes, in here, how is this particular, so I might have like taken a wrong example or something on this, I mean in this particular case, because this is not a BST property, right? Okay. I'm actually not really able to remember as to what did I teach at this particular point. I mean, what did I like try to express using this example. So probably I'll like rewatch this particular video and I'll address the problem in case there is any. Fine, so I'll surely like discuss this thing. So there is just one more question that I just want to like discuss with you, which you guys already know, but I just wanted to like just discuss it for the last time. So actually in AVL trees, in worst case and in best case, in worst case as well as in best case, in both the cases my searching operations takes only log n time. Fine, so I can write this as that my searching operation in AVL trees take theta of n, theta of log n time. But in case of BST, in the worst case, it will take order of n time, and in the best case it will take order of log n time. So we cannot write BST searching operation having a time complexity of theta of log n. So this is actually not possible. So if we have to like look at the options, we will come to know that A option is fine and rest all the other options are not really aligning well with the definition of or the property of AVL. Fine, so now we'll move over to heaps. So I'll move over to heaps right now. So in heaps, okay, so now we'll just discuss heap. So what are actually heaps? Heaps are a kind of priority queue. They are a kind of priority queue. There can be many other kind of priority queues, but heaps is one such kind of priority queue. But we don't really know as of now what priority queue is. But heaps were mainly designed to make this particular operation, get min or get max operation, done in the most optimal way. So let's say I'm having many elements coming or dynamically being generated, and I want to keep a track of this, that among all those elements, what is the minimum element. Although you can take one variable and just maintain that particular. So let's say I just give you an example that I'm having a stream of numbers, let's say 1, 10, 9, 8, 6 and maybe 2, and this is the stream of number, and I'm having a window of, let's say, 4 elements. Fine. So this is my window right now, and then this particular window reaches over here, and then this particular window reaches over here. So my window actually keeps on generating, and in every window I want to find out the minimum element. So this kind of problem, in where you want to get the minimum, or let's say if you want to get the maximum. So this kind of problems can be very efficiently solved using heaps. Fine. So let's say so I'll just try to give you let's say you are having a queue of students, 2, student 3, and all of them are coming in the class, or they are all of them are like coming into your class, and they are showing their report card, and you want to maintain a list of top 5 students. That's it. So that kind of things can be efficiently, this kind of problem can be efficiently solved using heap. Although you can like maintain 5 variables and then check. So let's say one student came in and he told us that there are that I have got 79%. Then what you can do is that you can compare them with all the 5 variables, and then into I mean whether he is getting more marks than any of those or not, and then you can like replace that. But heap would be a better option. Why? We will just discuss that how heap can be a better option for this. So in heap, actually get min operation can be performed in constant amount of time. Fine. So that is why it is considered a very good alternative for the example that I just discussed, that we are having numbers, a queue or a stream of numbers, and we find out the minimum in that particular window only, and my window can keep shifting. Fine. So in this kind of problems, if my get min operation is very efficient, then I can do solve these kind of problems in a very efficient way, and that is why we came across, or that is why we study heaps. Now heaps, I told you that heaps are a kind of priority queues. Now what priority queues are? Fine. So this is something that we need to discuss. Priority queues are, in my queue, in my regular queue, I am saying whosoever comes in first sits at the top. So let's say I'm having a bus, a queue for the bus, for onboarding a bus, and let's say Mr. Sharma came in first and he is standing at the top of the queue, and then Mr. let's say Gupta came in first, and then let's say Mr. Thukral came in at the third. So now whosoever actually came in first, he will be boarding the bus first. Fine. But in priority queues, every element is having a key attached to it. Every element is actually having a key attached to it. Let's say priority key attached to it. So let's say Mr. Thukral was a VIP person and he got the first priority. So he had the key where he said that I'll be having the first priority. So in that particular case, simple queues cannot really build we cannot really do any kind of modification to entertain this particular fact, that let's say in case someone is having a very high priority, then he should actually sit at the top of the queue and other people should sit next, and whenever bus comes in, he should board it first. So this is actually the concept of priority queues, that simple queues function on first in first out, that whosoever came in first will get the highest priority. This is how simple queues work, that whosoever comes in first will get the highest priority. But this is actually not the case with priority queues. In priority queues, every queue element will carry their own priority in the form of, let's say, number. In this, if we like talk of this particular case, so let's say the priority of this was 1, the priority of this was 2, and the priority of 3 was this, and in that way only they are processed. So let's say if after Mr. Thukral is processed, or after Mr. Thukral has boarded, then the element with the next higher priority should board the bus. So next Mr. Sharma should board the bus, and then only Mr. Gupta should be allowed to board the bus. So this is the like main thing about, or the main use of priority queues. So this priority queues is mainly a concept, fine. And how do we actually give an implementation of priority queues? That is with the help of heaps, fine. So that is why we will be studying heaps now, fine. So I just hope that I have made this clear, that why do we actually study heap. So now we'll discuss about heaps. Okay, fine. Okay, fine. So yes, so heaps, so now I actually told you this, that mainly heaps are the implementation of priority queues, fine. So they are the implementation of priority queues. Now how are they actually implemented? They are implemented, or they are stored in memory in the form of arrays. So heaps are stored in memory in the form of arrays, fine. And how do we do the visualization? How are heaps visualized? They are visualized in the form of complete binary tree. They are visualized in the form of complete binary tree, but in the memory they are stored in the form of arrays. So now I'll just show you how. So let's say I'm having an array and we are having a few elements in it. Let's say 1, 10, 8, 11, 12. These are the elements. Then if we have to visualize this particular array of elements in the form of a complete binary tree, then it will look something like this, that 1, whichever is the element at the top, should become the first or the root element. Then 10 should be its left child, and then 8 should be its right child, then 11, then 12. So this is how we visualize heaps in the form of, this is actually not a heap right now, okay, or this is actually even looking like a min heap. So there are many other properties that are related to heaps, but we'll discuss them one by one. The main thing is that how okay, so I just hope that I'm back. Maybe some like connection got lost, so now I just hope that it's visible. Okay, so I was discussing this thing, that now we do know that if we are given the parent index, then how do we find out the index of the children? But we also need to get this mapping also, that now we want this mapping also, that if we are having the index of the children, then how do we find out the index of the parent? So let's say that we are having the index of children or child node, and then we find out its parent, the index of its parent. Then how do this particular mapping happens? So let's say a child stored at the index I. So let's take this particular or let's take I is equals to 4. Then where is its parent stored, or at which index is its parent stored? Then its parent can be found out at this particular index. So 4 minus 1, which is 3 upon 2, which is actually equal to 1. Fine. So we actually simply take the floor of I minus 1 by 2. Fine. So if you take the floor of I minus 1 by 2, it will come out that the parent of 12 or this particular node is stored at index 1. So this particular mapping happens using I minus 1 by 2 and the floor of this, and this particular mapping happens by using 2i plus 1 and 2i plus 2 formula. Fine. So now you can like relate to this, that how heap are being stored in memory and how they are being visualized. Fine. So if that is clear, I just hope that everything is fine. Sir, please repeat. Okay, it was buffering. Okay. So I'll just repeat. Okay, fine. I'll just repeat. So I was saying that we were like just you must have like got this particular point by that time, that heaps are actually stored in memory in the form of arrays. Fine. But they are actually visualized in the form of complete binary trees. Fine. Now if we are having the index of a parent, so let's say if I am having an index equal to 2 or index is equal to 2, then where are, or at which index are its children stored? Then the left child, then the index of its left child would be 2i plus 1 and the index of the right child would be 2i plus 2. Fine. So if I have to give this for this particular node, which is I is equals to 2, its left child will be stored at 2 into 2 plus 1, which is 5, and its right child will be stored at 6, index 6. But here there are no 5 and 6, so this is how it is. Fine. So this is how we do the mapping, that let's say if we are given the index of the parent, then how do we find out the index of the children? But how do we do the vice versa mapping, that let's say if we are having the index of the child, then how do we find out the index of the parent? That is actually done using this particular formula, that if we are having the index of children as I, then you can find out its parent using this formula, I minus 1 by 2 and take its floor. So let's say if I want to find out that what is the parent of the child node which is stored at index 3. So what is the parent of 11? So what is the parent of 11? What is the index of the parent of 11? So I can actually find out using this particular formula. I'll just put in the value of I, which was 3. So 3 minus 1 is actually 2. 2 by 2 is actually equivalent to 1 only. Fine. So 3 minus 1 by 2 becomes 1. So basically its parent will be stored at this particular position. So I just hope that now you know that how do we how this particular relation works, that how heaps are actually being stored in the form of arrays, but they are being visualized in the form of complete binary trees. Fine. So now we'll be discussing about a few properties of heaps. So the very first property actually, so now let us just discuss that there are actually two type of heaps. One is min heap and the other one is max heap. So now let us just start with what min heap is. So in min heap there is one property. That property is as simple as this, that for every node n, both its children should be greater than n. Fine. So let's say if I am having this particular min heap 1, 10, 12, 11. So this is actually a min heap. Fine, because for this particular node both its child are actually greater than 1, and for this particular node there is only one child and which is actually greater than 10. So this is actually a min heap. And for max heap I have this property that for every node n both its children should be less than n. So if I have to give you an example of max heap, now if I have to like give that how is this particular heap being stored in memory, so this is how it is being stored in memory: 1, 10, 12 and 11. So you simply do the level order traversal of this particular tree and you will find out that how this particular heap is being stored in memory. Now if I have to take the example of a max heap, that would be 11, 9, 4. Okay, so it is not visible here, so I'll probably just draw this in a vacant blank space. So 9, 4, 6, 3, 2, let's say 1. So this is an example of a max heap. Fine. And how is this being stored in memory? In the form of array. This is how it is being stored in memory: 9, 4, 6, 3, 1, 2. Fine. So this is how this is how all this conversion works. Fine. So this is the main property of heap. Fine. So now let's say if we are having min heap, this particular heap, then how much time will it take to perform the get min operation? So let's say out of all these numbers, if I want to find out the minimum element out of all of these, then how can I do that? I'll simply return the element stored at the 0th index, because that will always be the minimum element. So basically get min in min heap can be done in order of 1. Fine. And similarly in max heap, get max can be done in order of 1. Fine. So this is how get min and get max time complexities work in get max operation works in min heap and max heap. So now we basically need to discuss that how do we actually do insertion in a min heap and how do we actually do deletion in a min heap. Now what do I mean by insertion? So let's say I'll probably take this particular space. So now let's say that I'm having this particular min heap which is looking something like this. Sir, index समझ नहीं आया, couldn't understand this particular example. Left and right child index समझ में नहीं आया. Okay, fine. So While all I was saying that is that, let's say if we are having any heap, so I am taking an example of min heap at this particular stage. So this is actually a min heap. Why? Because for every node, both of its children are actually greater than that node. Fine. Now actually this particular min heap in memory is stored in the form of array. So it will be stored in the form of array. This is how it will be stored: 1, 10, 12, 13, 15, 14. So you simply have to do the level order traversal. So this is how it will be stored in array. Now let's say if I have to find out that what is the left child, or what is the index of left child of node, let's say 12 or let's say 10. What is the index of the left child of 10? So how will we do that? We'll simply take the index of this particular node, which is 1, and now we know that its left child will be at the index 2i plus 1 and its right child will be at the index 2i plus 2. Now what is 2i plus 1? I will put in the value of I, which is 1. So 2i plus 1 becomes 3. So this is the left child of 10 and 2i plus 2 is 4. So this is the right child of this particular node. Fine. So you can like directly see this in heap. If you are like having the visualization of the heap in the complete binary tree form, then you can right away see this. But in case you are having the arrays, because eventually heap are being stored in the form of array only. So if your program wants to see that what is the left child and the right child, then this is how you will find out the left child and the right child. Fine. So now we were like discussing this thing, that how do we do the insertion and deletion in heaps. Just give me a second. I'll just clear this off. Fine. So let's say if I want to insert one new element, let's say if I want to insert 9 in my min heap, then how do I insert 9? So for the insertion, we use only one operation. Okay, so there is one important operation which is being used in insertion, and that is percolate up operation. And in deletion, we actually use one important operation, that is to percolate, that is called percolate down operation. Fine. So इंसर्शन में परकोलेट अप का यूज़ करते हैं और डिलीशन में परकोलेट डाउन का. अब ये परकोलेट अप होता क्या है वो हम डिस्कस करते हैं. सो नाउ विल बी डिस्कसिंग अबाउट व्हाट एक्चुअली परकोलेट अप इज. So let's say whenever a new element comes in, so my array representation of this was looking something like this: 1, 10, 12, 13, 15, 14, and then a new element came in 9. So 9 will actually be stored at the end in the array, and if I have to visualize this in complete binary tree, it will be stored in here. Fine. So now after we have stored or my new element over here, then we simply need to percolate up. What do I mean by percolate up? From this particular, from the newly inserted node, you trace it back till the root. You trace it back till the root and you check, because this is a min heap, you check that whether this element is smaller than this or larger than this. If this particular element is actually smaller than this particular element or its parent, then you actually swap them. So in Percolate Up, you actually compare the child node with parent node, and if my child node is actually less than my parent node, then we swap the data of these two nodes. Fine. So if for this particular insertion, so I'll just clear it up a bit, and then I'll show you that how do I do the Percolate Up thing. So now I'll basically compare 9 with its parent, which is 12. So I'll compare the newly inserted node with its parent. Fine. How do I find out its parent? Using I minus 1 by 2, this in array, this is how I find out. But over here I can right away see this visualization, so I need not use this particular formula. So I can see that 12 is actually greater than 9, so I need to swap. So 9 will come in over here and 12 will come in over here. Fine. So now 9 will now be compared again to its parent. So now 9 is compared with 1, but already 1 is actually less than 9. So we need not percolate my newly inserted node up any further. So I need not percolate it up any further, and this is where I will stop. Fine. So now let's say that I give you this thing that I have to insert 0. I have to insert a new node which is 0. Then how do I do that? So I'm just like making some space. Fine. So now I need to insert 0. So where will I insert 0? In my array it was looking something like this: 1, 10, 13, 15, 9, 14 and 12. It was looking something like this, and whenever my new node is inserted, it is inserted always at the end. Fine. So 0 will be inserted over here, and in my tree this is where it will look like. So if I have to like see this, that the parent of 0 is actually 13. So even if you have to like find this out, you can do this using that particular operation: 7 minus 1 by 2 floor. So this is 6 by 2, which is 3. So this is, okay, this is not, this shouldn't have been 0, 1, 2, 3, 4, 5, 6, 7. So it should have been the parent of this. Are we doing something wrong? 0, 1, 2. Okay, sorry. Okay, I just like, this particular thing is not right. This particular thing is not right. I did something wrong over here. I did not like write the array in the right form, because I have to do the level order traversal, right? 4, 5, 6, 7. So the level order traversal would be 1, 10, 9, keep percolating it up. This is how my insertion happens. Fine. So now we'll just try to find out that how do my deletion works in heaps. So in case you are having any problem, any buffering, Just give me a second, I'll just. सौरभ, ये नेट चल रहा है? Okay, so it is fine now. Okay. Actually वो कॉल आ गया था किसी का फ़ोन पे, तो वो नेट अपने आप ऑफ हो गया. So I just hope that it's like it's clear now. Okay, so so Sakshi was asking this, that whenever we perform percolate up, एरे में चेंज नहीं करते उसकी पोजीशन. हाँ साक्षी, एरे में भी चेंज करते हैं उसकी पोजीशन, बट द थिंग इज़ कि मैं अभी सिर्फ विजुअलाइजेशन की फॉर्म में उसको शो कर रहा था और उसकी फॉर्म में शो नहीं, मतलब एरेज में मैं डिफरेंस नहीं दिखा रहा था. मैं एरेज में नहीं दिखा रहा था, अभी मैं सीधा ट्रीज़ में ही करी जा रहा था, क्योंकि अगर आपको पेपर में भी वो क्वेश्चन कोई पूछेंगे तो पहले आप उसका कंप्लीट बाइनरी ट्री बना लीजिएगा और उसके बाद कीजिएगा. फाइन. तो जब भी मुझे whenever I have to do insertion, I simply perform two things. First is that you add that particular element to the end, or whatever is the new element, you add that particular new element to the end, and then you keep percolating it up. ये arrays में भी सारी positions change होती है, बट मैं दिखा नहीं रहा क्योंकि उसमें ज़्यादा टाइम लग जाएगा. और अगर आप को पेपर में भी जाना है तो पेपर में भी आप कंप्लीट बाइनरी ट्री की, मतलब ये विजुअलाइजेशन बना के ही इसमें चेंजेस करके आप आंसर दे सकते हैं. फाइन. सो अब आफ्टर डिस्कसिंग दिस इंसर्शन थिंग, विल नाउ मूव ओवर टू हाउ डू वी डू द डिलीशन इन माई हीप्स. फाइन. यार, इज इट वर्किंग? Is it audible now? I mean, I just. So is it like working now? Still buffering. Buffering again. Just give me a second. I'll just. Okay, fine. Still buffering. I hope that it will not buffer now. Fingers crossed. Okay, fine. If it is fine now. Okay, if it is fine, then we'll just move ahead. So we were like done with this thing, that how do we do insertion in heaps. So now we'll be discussing about how do we do the deletion in heap. So in deletion, for the deletion, I actually told you this. Okay.
The internet is working fine.
Why is this problem still existing?
सही चल रहा है.
इसमें बफरिंग हो रहा है, बफरिंग. कुछ भी मैं खोल रहा हूँ ना, जैसे कि देख फेसबुक खोला या फिर कुछ भी,
यहाँ पे तो यूट्यूब पे वीडियो चलती है ना.
इसमें नहीं चल रही है. एवरीथिंग एल्स इज ओपनिंग बट यूट्यूब में कुछ पंगा आ रहा है, पता नहीं.
रिस्टार्ट कर लो सेशन ही में.
रीस्टार्ट कैसे करना है?
नीचे वो तो डालने की.
Okay, looks like will work fine now. To restart the session, the streaming software again and again, but कुछ